Hi there. This video is on section 10.3. We're going to be doing a couple things in this section. We're going to be writing functions and non-functions as polar equations. I had to define what a polar equation. I'll do that in a moment. And then we're also going to find derivatives in these polar equations. So polar equations is just basically a special version of parametric equations. When we did parametric equations in 10.1 and 10.2, we used the letter t as the parameter, and we wrote x in terms of t, and we wrote y in terms of t, and t was just that time step variable. In polar equations, we have two parameters. So we're not going to be using t anymore. We're going to be using two very specific and special parameters, r and theta. And we're going to be transforming our normal rectangular graph into a sort of radial graph. Right? I'll show you what that looks like in a minute, but we're going to be using r and theta, and these relate directly to sine and cosine. So if you do remember your trigonometry from pre-calculus, it'll be very helpful. If you don't, that's okay. You just have some more to review. But this is deeply embedded into what you did in pre-calculus. Okay, so we have r and theta. Both parameters are going to be used in place of x and y. So we have a normal xy equation. We're going to be parameterizing it in terms of r and theta. I'll show you some examples of that. There are some very, very important formulas, or at least relationships, between x and y and r and theta that will always be true. And these are straight from, as I mentioned, trigonometry. So over here on the left-hand side, we always have x as r cosine theta and y as r sine theta. That's just the definitions of x and y in terms of r and sine and cosine from trigonometry. And here on the right-hand side, we have r squared equals x squared plus y squared. That's basically the Pythagorean theorem. And we have tangent theta is y over x, which is just your opposite over adjacent formula for tangent, using y for the opposite and x for the adjacent. Essentially, what you can see is on this side over here on the left-hand side in green, if you're color sighted, this is a way of finding x and y if we're given r and theta. If we're given what r and theta are, you can plug them in and find x and y. And over here on the right-hand side in blue, these are the ways of finding r and theta. If you know what x and y are, you plug them into the right-hand side. On the top one, you'd have to square root to find r. On the bottom one, you'd have to take the inverse tangent to find theta. But these are the ways to find r and theta if you are given x and y. So they're basically ways of relating the two different types of equations, the Cartesian equations with x and y, and these polar equations with r and theta. Okay, so I've given just a simple of example of a polar equation. This has an equivalent Cartesian equation. That's the one right down here. These equations are identical. I'm not going to show you right now exactly why they're identical, but I'm just trying to show you an example of the parameterization, the polarization. We took a nice normal Cartesian equation. This is actually a line, y equals 2x plus 3, and we rewrote it using these polar equations, these polar parameterizations of r and theta. It looks much more complicated, of course. R is equal to 3 divided by sine theta minus 2 cosine theta is the equivalent polar equation to y equals 2x plus 3. We can show you why that's going to be. I just don't want to get ahead of myself too much. So you have to take my word for it for the moment. Why would we do this? Why are we taking something like y equals 2x plus 3, very nice simple equation, and trying to write it in terms of this crazy sine cosine parameterization with r's and thetas? Well, for a line, I think lines are much better worked with in Cartesian equations. So you probably would never have a need to convert a line into a polar equation. But there are some very complicated equations in Cartesian coordinates that are much, much easier in polar coordinates. So as soon as you get curvy things and cycling things and non-function things, you're going to be very happy that polar equation parameterizations exist, because working with the Cartesian equations is kind of a nightmare. So definitely has its use purposes, and we're going to be showing some examples of that. Just some vocabulary for you, because it'll come up. The parameter r is called the radial distance, or the radius. which is the distance from the origin. So if you start from the origin, and if you go out a distance of 2, this would be an R value of 2. And it doesn't give a direction. So an R value of 2 doesn't tell you where you are necessarily. It just tells you you're 2 from the origin, wherever direction you went. The other parameter, the other variable, is going to be called theta. So R is your radial distance or radius. And the other variable is theta, and that's the angular coordinate or the angle. And that tells you how far you go. And just like in normal trigonometry, we always start measuring the angle from the positive x-axis. So this would be theta here, or this would be theta here, right? So depending on your theta, your going out to would be in a different location. If you know how much you rotate around the circle and you know how far you go out from the center, that will identify a particular point. This point here, for example, if we know this first theta, or any other point depending on what theta you're given and what radius you're given, what radial R value you're given. All right, so those are just the vocabulary that you'll be noticing when doing problems and read book, etc. All right, let's start getting some just basic ideas, examples done, so we're not just so theoretical talking about everything. I'm going to be referring to these 4 equations up here over and over and over again. So if you don't have those memorized, I would definitely recommend writing them down, because no matter what page we're on, we're going to be using those 4 formulas. And I have them memorized, and I'm going to maybe flip back a couple of times, but I really want you to have them ready, because we're going to need them on most problems. So we're going to kind of remember those green and blue, the x equals r cosine, y equals r sine, and the r squared equals x squared plus y squared. The tangent is equal to y over x equations, right? Okay. So with that said, let's start looking at some specific examples. So example A says, convert the following r theta polar coordinates to Cartesian coordinates and also graph the points. So it gives us 3 comma pi over 2. That's r comma theta. So we know the r is the 3 and the theta is the pi over 2. It's always r first and theta second, just like it's always x first and y second, right? So we're going to have to write the x and y coordinates if we're only given r and theta. All right, how do we do that? Well, if you guess these equations up here, you guessed correctly. And the ones on the left are how we get x and y given r and theta. So we're going to be using these ones right up here. The x equals r cosine theta. And y equals r sine theta. So, well, let me just move those over a little bit, just so I have space for the next problem. X equals r cosine theta, and y equals r sine theta. And we literally just plug stuff in. So we know r is 3. We know theta is pi over 2. And same thing with y. We know r is 3. And theta is pi over 2. So you'll have to remember your basic trig calculations. There's like 5 trig values that we want you to memorize. 0, pi over 6, pi over 4, pi over 3, and pi over 2. And these are pi over 2s. If you don't remember it, that's okay. Grab a calculator or grab some notes so that you can begin to memorize those basic calculations. It's just so much easier if you know that the cosine of pi over 2 is 0 instead of having to look it up or use your calculator every single time. So this is 3 times 0, or just 0. And sine of pi over 2 is 1. And so that's y equals 3 times 1, which is 3. So we know the point is 0, comma 3. So 0, comma 3, I'm not sure where to put it, maybe over here, would be the x, y coordinates that match with 3, comma pi over 2. And then we're going to repeat those with these other ones. So if you want to try to remember how to do those, good time to pause and try it. And I'm going to write these out, and then we're going to graph them. So pause if you will, and then I'll show you the solutions here. So I'm going to use the same, maybe I'll just write the formulas up here. X equals r cosine theta, and y equals r sine theta. and I'll just start plugging in over here. So x equals r. R is -1 cosine of pi over 4. And what does y equal? Y equals r. That's supposed to be an r over here. So y equals r, again, -1 sine pi over 4. So x is equal to -1 times 1 over root 2, or root 2 over 2. And y is equal to, well, the same thing, -1 times sine pi over 4. Sine pi over 4 is also 1 over root 2. So we get our xy coordinate of -1 over root 2, comma, -1 over root 2. So that's the point -1, comma, pi over 4. So the r value is -1, and the theta value is pi over 4. And lastly, smidgen right here, I get x is equal to, okay, let me move this over a little bit. And let me use a different color. Okay, so x is equal to r cosine theta. Y is equal to r sine theta. All right, so then we have to learn what the cosine of pi over 3 is. If you're wondering how I remember these things, right, the cosine value and the sine value are just points on a unit circle. So if you imagine a unit circle goes to 1 and -1 and -1 and 1. When we have an angle of 0, we're right here. This is where theta is equal to 0. We haven't gone anywhere off of the x-axis. The x value is 1 and the y value is 0. Well, we know x is cosine, so cosine theta, or cosine, excuse me, of 0, because we're at angle 0, is equal to 1. And we have sine of 0 is equal to 0. If we're up here at the peak, this is where x is 0 and y is 1. So we know here, which is, this is pi over 2 radians. I'm going to move me over here. So for pi over 2 radians, we would know that the cosine of pi over 2, which is the x value, is going to be 0. And the sine of pi over 2, which is the y value, is going to be 1. Right? And then for anything in between, like for pi over 3, well, I just say, okay, this is pi over 6, pi over 4, pi over 3. Right? So that's just the different values. So right here, we need an xy coordinate. And once you've been doing these a few times, you remember what they are. The x coordinate is root 3 over 2. The y coordinate is 1/2. So for cosine pi over, oh, that's pi over 6. I want pi over 3, is that right? Yeah. So pi over 3 is this one up here. Let me do a different color. So pi over 3 is this one right here. Pi over 6 was the one I did before, which I thought we were using, but we're using pi over 3. So pi over 3 is right over here. The x value is 1/2. The y value is square root 3 over 2. So for pi over 3, the cosine, the x value at that radial measurement is 1 over 2. So x is equal to 2 times 1 over 2, or x is equal to 1. And y is equal to 2 times sine pi over 3 is the y value. The y value at that radian is root 3 over 2. 2 times root 3 over 2 is just root 3. So we got the x value of 1 and the y value of root 3. All right, so that is converting from polar coordinates to Cartesian coordinates. All right, so let's see what they look like graphed. All right, so I have here two different versions. I have an XY graph, which is rectangular, and then we have the R theta graph. So this is the R theta world over here. We don't really have an R axis and a theta axis in the same way that we have an X axis and a Y axis. Theta is rotational. It's how far we go around, and R is how much we go out from the origin. So let's see what that looks like. So for the first example, 3 comma pi over 2, the R is 3, so I'm going out 3, and that's at an angle of pi over 2. So I have to find my angle of pi over 2, which is right here. Here's my angle pi over 2, and I go out 3. 1, 2, 3. Assuming these are counted by ones. So this is 1, this is 2, this is 3. That would be 3 comma pi over 2. I've gone out 3 at an angle of pi over 2. And that's this point right there. Maybe I'll get rid of these other little hash marks so it's not so confusing. That's 3 comma pi over 2. We said, by the way, that that was equivalent to 0 comma 3. In the rectangular world, in XY world, 0 comma 3 is x is 0, y is 3, and it's the same location. 0 comma 3 and 3 comma pi over 2. Next one we have is -1 comma pi over 4. So the angle is pi over 4. There's pi over 4 right here. And the R value is -1. So instead of going 1 out, we're going to go 1 backwards, right? So instead of going out 1, we're going to go backwards 1 because negative is just reverse the direction. And that would be right here. That would be our angle of pi over 4, but going backwards -1. And our Cartesian coordinate would be -1 over √2 and -1 over √2. 1 over √2 is about 0.7, so it'd be somewhere right around, well, right around there. So somewhere right around here. I guess it's in green over here. You can tell it's in the third quadrant in both situations. And lastly, I'll just do it real quickly. We have 2 comma pi over 3. So I got to find pi over 3. Maybe I'll do this in black. Pi over 3, and I go out 2, 1, 2. That would be 2 comma pi over 3. Pi over 3 angle, go out 2. And that should be the same thing as 1 comma √3. So 1 comma √3 is about 1.7 or 1.8 maybe. So it goes like right here. And hopefully those match up. So that's visually and sort of algebraically looking at the conversion of polar coordinates to Cartesian coordinates. All right, let's do a little more practice going the other direction. So the other direction, we have some XY coordinates. We want to convert them into Cartesian coordinates. Okay, so how do we do that? Well, I'll flip back and remind you. We have these 4 equations. Let me zoom in a little bit here. And we're not going to forget those, right? We're going to write them down or memorize them if you haven't already have them memorized. The ones here on the left are, if you're given r and theta, you can get x and y. The ones on the right, if you're given x and y, is how you get r and theta. So I'll be using the ones here on the right. I'll write them up here, I guess, just so that I have them handy. So I got r squared. I'm going to do something that stands out more than black there. So I get r squared is equal to x squared plus y squared. And a tangent, which basically measures the slope, by the way. If you didn't know, tangent really measures the slope. It's like change in y over change in x, which is what the tangent is, rise over, opposite over adjacent. So tangent is y over x. Okay, so we are given some xy values. It says we're given xy values, and we want to find the r theta values. So for the first one, to find r, we're going to write r squared is equal to x squared plus y squared, which means r squared is equal to 4 plus 4, which is 8. And so r is equal to plus or minus the square root of 8. We do have more than one option for r, and that's actually also going to be true for theta. Actually, let me just move this over real quick, just because I know I'm going to run out of room. Sorry about that. R squared equals x squared plus y squared. So r squared is equal to -2 squared is 4 plus 4 is 8. And that means r is equal to plus or minus the square root of 8. All right, so what is theta? So we know theta is, well, we know tangent theta at least is y over x, right? Y over x. So I take the y value, divide by the x value. That is tangent theta, y over x. So tangent theta is equal to 2 over -2 is just -1. And so theta is just going to be the inverse tangent of -1. So now again, we have to go back to our, pre-calculus work and saying, what's the angle where the tangent is equal to -1? The tangent's really the slope, if you remember. So where is the slope -1? Well, the slope is -1 is like a 45 degree, a perfectly diagonal line going down. So the angle over here, 1 pi over 4, 2 pi over 3 pi over 4, 3 pi over 4 is the angle in which you have a slope, a y over x of -1. But we also have another one over here. So 0, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 7 pi over 4. 7 pi over 4 is also an angle in which it has a tangent. It has a y over x to be -1. We have another one. We can go full circle, which is 2 pi plus another 3 pi over 4. So 2 pi plus 3 pi over 4, right? This is 8 pi over 4, by the way. So you get a total of 11 pi over 4. So if you go around the circle, which is 2 pi, and another 3 pi over 4, you end up with 11 pi over 4, which is also an angle theta, which has a tangent of -1. It has a y over x. In fact, there's an infinite number of angles. So we're going to get angles such as 3 pi over 4, 7 pi over 4, and then we get 11 pi over 4, and we get 15 pi over 4. You can also do negatives because you can rotate in the opposite direction. Negative just means go in the opposite direction. So we get something like -1 pi over 4, etc. So you get a lot of different angles that match up and a lot of different R values that match up. In this case, 2 R values that match up. So there are many, many ways of writing this -2, 2, this x, y value in terms of polar coordinates. And so you have to sort of keep track of which things match up. So if you're using a positive R value, let's say square root of 8, right? So we're going in the normal direction, we're not going backwards, right? Then which angle is going to give us a slope of a y over x value of -1? Well, there are several of them. You can go, so let me graph this -2 comma -2. So -2, -2 comma 2 is right here. So we want a point that ends up with there. So if we do a radial value of square root of 8, which is, the diagonal here, right? 2.3 something, right? Then we want the angle to be in the third quadrant. So that's 7 pi over 4. So 7 pi over 4, no, 1 pi over 4, 2 pi over 3 pi over 3 pi over 4 is the angle right here. And we go out a distance of square root of 8, which is, 2.7 or something like 2.5 or something like that. So that would be 1, 2.5. So that would be that dot right there, which is supposed to correspond to this dot right here. So this is the the -2, 2, the version in the Cartesian world. And this right here would be the R value is square root of 8, and the theta value is 3 pi over 4. Now, I just want to emphasize that there's more than one correct answer for this. So for this one, we could have gone around the circle again. So the same square root of 8 for R, but going around and again 3 pi over 4, that would be our 11 pi over 4. So that's the one we got over here. We went 2 pi plus another 3 pi over 4. So that would be 11 pi over 4. That's also a correct R comma theta value that lands exactly at this point right here, which corresponds to -2 comma 2. And we can also go backwards. So suppose we were going like this angle over here, which is 7 pi over 4. So 7 pi over 4 could be the angle. But if we had 7 pi over 4, we're in the wrong quadrant, right? 7 pi over 4 is in that fourth quadrant. We need to be in the second quadrant. So we need a negative square root of 8. So we're going backwards. The radial measurement is not going, into the fourth quadrant, it's going backwards into the second quadrant. So this also is another way of labeling the point -2 comma 2, negative square root of 8, and 7 pi over 4, etc. So be aware, there are many possible answers, and this will come up in different ways. So the first answer isn't always going to be the one that you need for a particular application. So you are warned. All right, this all comes from pre-calculus. If you did pre-calculus, you solved equations, you may remember getting lots of different theta values for your answer because of periods and rotations and things like that. Okay, let's do a couple more examples here. 0, 3. So we know how to find r squared. We know how to find tangent theta, right? And these are all just the same kind of thing. So I'll do another one. R squared is x squared plus y squared, which is going to be just 9, and r is equal to plus or minus 3. And our tangent theta is y over x. So our y is -3, our x is 0. Oh, this is undefined. So when is the tangent of an angle undefined? What angles make the tangent undefined? Well, go back in time if you need some help. I can't redo all of pre-calculus, but I could just kind of allude to the things that you've done before. That may have been quite a while, so you may have a distant memory of these things, but we do need them to come back. Tangent is undefined at pi over 2, 3 pi over 2, etc. So we know the angle here is either pi over 2 or 3 pi over 2, something like that. We want 0, -3, which is down here, sort of between the third and fourth quadrants. So if we did pi over 2, we'd be sort of in the wrong place, right? Pi over 2 is here, so we'd have to have a negative r. So for this guy, we would have pi over 2 as our angle, and then the negative r, which would be -3. So down here would be our value of -3 and an angle of pi over 2. Because pi over 2 is here, but instead of going radial out to pi over 2, we're going in the reverse direction away from pi over 2. So that's how we get there. You could also do the angle 7 pi over, or the angle 3 pi over 2. So 3 pi over 2 could be the angle. In this case, we need a positive r, a positive 3. So in the direction of 7 pi, or the direction of 3 pi over 2, you're going out 3. All right, and lastly, we have 3, 4, which I don't have a space for. And it's the same kind of thing. So if you want to try that exercise to see if you can come up with the possible, r theta values for 3, 4, I'll do it right here. Okay, so for inverse tangent of 4 over 3, this is not one of the angles that we ask people to memorize. It's not like 0 or pi over 6 or pi over 4 or pi over 3 or pi over 2. So we're going to use technology to find the inverse tangent of 4 over 3. So inverse tangent of 4 over 3. And it gives us about 9.927. And it definitely needs to be in radians. It does give degrees, but we need to stay with radians when we're doing calculus. So don't give the degree answer. You want the radial answer. So 0.927 approximately radians. So that would be a little bit less than 1 radian, right? We know that in a circle, right, we have 3 radians is over here. It's pi. Pi over 2 is about 1.5 radians. 0 is 0 radians. So 1 radian would be somewhere in between. I don't know where it is. Okay, let's say it's here. That's the radian measurement of 0.927. And I'm giving you a circle as a visual aid just to remind you that there's more than one answer. So we could whip around and go here, like another pi over 2. So pi over 2 would be 0.927 plus pi over 2. And if you want that as a decimal, you could just throw that into a calculator. Pi is 3.14, etc. Divide by 2, add 0.927, and that would be next theta value. And we can get more theta values because remember, we can go multiple times around the circle. So we can go 2 pi, which would be a full rotation, plus 0.927. Or we could do our 0.927 plus pi over 2, which was down here, plus 2 pi, just go another way around the circle. There's lots and lots of different angles that all will give you that same location. And then we just have to find the one that matches up, right? If we're doing the 0.927 and we want to reach 3 comma 4, we need the positive r value. So that will give us a positive 5 and a positive 0.927. If you're doing the pi over 2 version, if you're doing the 0.927 plus pi over 2, which is your angle in the third quadrant, then a positive r value would keep going more and more in the third quadrant. We don't need that. We need it to go in the reverse direction into the first quadrant. So we would need a negative 5 for the r value for that one. And you can play around with more of them if you like. So those are some examples of converting the XY coordinates into polar coordinates. Didn't do all the graphing, but let's do 3 comma 4. 3 comma 4 would be x is 3, y is 4. And then the r comma theta we did was, let's say, well, we know the theta was like 0.927 and the r was 5. So I don't know where, let's see, pi over 3 is pretty close to 1. Pi is 3.14 divided by 3. So that's a little bit more than 1. So I need to go a little bit like over here. So this is like where 0.927 is. And they got 5. 1, 2, 3, 4, 5. Let's see. 1, 2, 3, 4, 5. So right here might be our R value of 5 and our theta value of 0.927. All right, so maybe this was tedious. I'm not sure how educational this was for everyone, but I did want to show you visually what's going on here and also algebraically how to convert between XY coordinates and R theta coordinates. You don't do a lot of this in calculus, but we do have to understand polar coordinates and polar equations. And part of just understanding the stuff is just doing some calculations and seeing the difference between X's and Y's and R's and thetas. So this is an attempt to help you kind of see the idea behind the R theta thing. All right, let's get into some more mathy kind of calculus stuff that we can do with polar equations. All right, so after my A-B examples where I was just trying to convert stuff and graph stuff, let's actually convert an equation. So this equation is R is equal to square root 25 over cosine squared plus 3. We're going to convert this into a Cartesian equation. So how are we going to do this? Well, we want x's and y's, right? We want x's and y's. And you remember that if you know like x equals r cosine theta and y equals r sine theta, this converts thetas and r's and x's and y's. And you can also use the whole idea of r squared is equal to x squared plus y squared. And that tangent theta is equal to y over x. That will also convert x's and y's into r's and thetas. And you can use any of these equations anytime. They're all true always with polar equations. All right, so we have a square root here. Don't like square roots. They're hard to calculate. We have an r. Maybe notice that r squared is a thing that easily converts into x squareds and y squareds. So I'm going to square both sides of this. That simultaneously makes the r into r squared and gets rid of the square root. Okay, so basic algebra, simplify. Let's simplify some more by getting rid of the fraction. So I can just multiply by this cosine squared plus 3 on both sides. I'm going to multiply it on the right side and the left side. I'm just going to do this times the whole thing. On the left-hand side, I get r squared cosine squared theta plus r squared times 3. I'll write the 3 in front. Then multiply the whole thing by r squared. On the right-hand side, the cosine squared theta plus 3 divided by cosine squared theta plus 3 equals 1. So I'm left with just 25. All right, so now I have no fractions, no square roots, nothing fishy going on. I can start converting stuff. So remember that we can use this right here to get x's. R cosine theta is equal to x. And we have r squared cosine squared. I'm not sure if people can read that. It says r squared cosine squared. I'll write this as r cosine theta all squared, right? Because r squared cosine squared is just r cosine theta squared. And we know what r cosine theta is, just x. So this is r cosine theta, or x, being squared. Right? So this is just x being squared. We have 3r squared. We do know what r squared is. R squared is given by x squared plus y squared. So we can just rewrite everything. We know that our r cosine theta is x, so it's x being squared. We know that r squared is just x squared plus y squared. And there's a 3 in front of it, so I'll put the 3 in front of x squared plus y squared. And then that's it for the left-hand side. Is get 25. Okay, and now I can just combine things together. I get x squared plus 3x squared plus 3y squared equals 25, or a grand total of 4x squared plus 3y squared equals 25. And that's a nice simplified form to leave the Cartesian equation that came from the polar equation, r is equal to square root of 25 over cosine squared theta plus 3. Okay, and then of course we can convert not only a polar equation into a Cartesian equation, but we can also convert a Cartesian equation into a polar equation. That is example D. Same equations we're going to be using over and over again. We just got to figure out how to do it. So, well, one thing we can see kind of is that x squared plus y squared is always r squared. So if I rearrange this thing a little bit, x squared plus y squared right in front minus x equaling 0, then this thing right here, I know it's got to be r squared. That's going to be r squared. R squared. And then what about x? Well, we know what x is. X is r cosine theta. So this is r cosine theta equals 0. Hey, that was kind of nice, right? So look out for those things. And you can rewrite everything in terms of r's and thetas. This is a nice simplified version of this. You can also factor it if you like. There's different ways of rewriting this. That seems fine to me. So that's an example of converting a Cartesian equation into a polar equation. Okay, we got one more set of examples. We're going to do some more conversions, and we're going to do some derivatives and things like that. So I have a convert into Cartesian equation and a convert into a polar equation. This is the same as what we did in the previous two examples, or what I did in the previous two examples. So this is a great opportunity for me to remind you to give these things a try if you are willing. See if you can remember the formulas and how to use them to convert things in there. And then come back after you've paused, pause the video and come back after you've finished so that you can see if your answers align with what I'm doing here. Okay, so if you're back or if you just stayed to see what I'm doing here, I'm going to be solving both E and F. All right, so I need a Cartesian equation. I have cosecants and cotangents. My formulas involve sines and cosines, so I'm just going to rewrite these things using sines and cosines. So cosecant is 1 over sine. Cotangent is cosine over sine. So now they're in cosines and sines, which I definitely prefer. I'm gonna let's see, multiply both sides by sine squared. So I get r sine squared theta is equal to, and that's a multiplication, to cosine theta. Let's see what I can do. Well, let me write down my formulas. R is equal to cosine. x is equal to r cosine theta, y is equal to r sine theta. I do have an r sine theta, but I have an extra sine theta in there, which is a little bit annoying. And then I don't have any r squareds or x squareds or y squareds, so that I think I'm using that this time. But the other one I have is tangent of theta is y over x. And I do think I can get a tangent theta out of here. So check this out. I'm going to divide by sine theta. Why am I doing that? Well, I have r sine theta. Actually, you know what I'm going to do? That's what I'm going to do. I'm not going to divide by sine theta because there's a problem with sine theta equaling 0 and dividing by 0, stuff like that. I'm going to do something smarter. I'm going to multiply both sides by r. I'm going to multiply this by r. The problem I had was that I had only one r and basically two signs, like sine squared means sine times sine. And I have to have the r sign paired up, right? I have to have r and sine to convert to y. So if I multiply by r on both sides, then I have r squared sine squared. And that I can convert because each r sine is just going to be y. On the right-hand side, what do I have? I have 2r cosine theta. Oh, and that's good too, because r cosine theta is just x. Okay, so this guy right here is going to be r sine theta, r sine theta. It's going to be y squared. On the right-hand side, I have 2 r cosine theta. R cosine theta, without the 2, r cosine theta is x. So it'd be 2x. And that's it. That's my equation in terms of x's and y's. There are other ways of doing it. Like you could have divided by sine and just made a qualification about not dividing by 0. But this was a trick, I think, if you found it, was actually pretty neat because it avoids all that division and makes it pretty easy to convert. No matter which method you use, you're going to get the same equation. You're going to get y squared equals 2x. Okay, lastly, I'm going to convert this guy in f. Again, I don't like square roots, so I'm going to square both sides. I have to get polar equations. I have x squareds and y squareds, but they're on different sides of the equation. So what I'm going to do here is maybe make something where I'm going to get an r squared. So maybe I'll just add x squared to both sides. Seems kind of funny, but I'm just trying to make it so that I have things that I can convert. So x squared plus y squared is definitely r squared. So I know that one. On the right-hand side, I have x squared plus 3x squared, which is 4x squared plus 4. And I know what x is. X is r cosine theta. So this thing right here, I still have r squared on the left. I have 4 times x squared. So x squared is 4 squared cosine squared. And then I have a plus 4. And now I have all my r's and thetas. As long as I simplify this, I will have my polar equation. 4r squared cosine squared theta plus 4. So I guess I can bring the r squareds to this side. R squared minus 4r squared cosine squared equals 4. I can factor out an r squared. And then I can divide both sides. I'm just solving for r squared. So r squared is equal to 4 over 1 minus 4 cosine squared theta. And I think I should leave it like that. I guess you could take the square root if you wanted to get r by itself, but you would get a plus or minus because of absolute values. I'll just leave it as r squared equals 4 over 1 minus 4 cosine squared theta as a version of simplifying this into a polar equation. All right, we got 2 last examples for you before the end of the video. I've very creatively labeled them examples G and H. So G says find the derivative of r equals 4 sine theta. So we want to find the derivative dy dx, and we have no y's and no x's. We just have r is equal to 4 sine theta. So what the heck do we do there? I know we got all these derivative formulas, but how do we do them in this particular situation? Well, for this one, I'm going to remind you about, the way we did parametric equations. The way we did parametric equations is you just differentiate with respect to t. So, for example, we did like dy dt over dx dt, right? That's how we did parametric equations. That gave us dy dx. I mean, we don't really have t this time. We have to do a different version, but we're going to do something very, very similar. We need to differentiate this respect to theta. So we're going to do dy d theta over dx d theta. That will give us dy dx. All right, but once again, we don't know what y is, but we do know that y, did you forget, is always r sine theta. So this is the derivative of r sine theta. And the bottom is the derivative of x, which is the derivative of r cosine theta. All right. So at this point, you have a choice. We know what r is. R is this critter right here. We're told specifically r is sine theta. So you can stick this in right here and, of course, right here because you know what r is. And then you would just get the derivative on the top of 4 sine theta times sine theta. And on the bottom, you get the derivative of 4 sine theta times cosine theta. So you can stick in the r right now and differentiate them. The way their textbook does it is they first find the derivative and then substitute the r in. So I'm going to do it the way the book does it just because I want to align with that a little bit. Personally, I usually just plug in the r right away and differentiate it, but I will show you the way they do it. It does another little thing which it reminds you about the chain rule and about implicit differentiation. So that's another sort of reason why I wanted to do it along with the way the author of your book does it. So how do we do this? Let me use a different color over here because this is going to get in the way. All right, so how do we differentiate r sine theta? Well, r is a variable, we know that. It's the radial distance, and theta is a variable, we know that. It's the angular distance or angular measurement. So this is a product rule problem. So to do the product rule, we do the derivative of the first one times the second one plus the derivative of the second one, derivative of sine is cosine, by the way, times the first one. So that's the product rule on the top. On the bottom, also another product rule, the derivative of the first. Remember we're differentiating like the theta, right? So d theta is on the bottom, right? Derivative of the first times the second, and then plus the derivative of the second. Well, derivative of cosine is minus sine, so I'll do a minus here. Minus sine times the first. So that's just what the derivative is using our favorite formulas of x equals r cosine theta, y equals r sine theta, differentiated using the product rule, the chain rule, implicit differentiation, all the things that you've learned in calculus are all kind of coming together to make sure that you can do these kinds of problems. All right, so then what we do is we're just going to substitute in. We do have to know what dr d theta is, so I'm going to do that over here. If r is equal to 4 sine theta, and I differentiate this whole thing with respect to theta, then on the left-hand side, I get dr d theta. On the right-hand side, the only variable is theta, so it's very easy to differentiate. I just get 4 cosine theta. So this is what my dr d theta is. I already know what my r is, so I'm going to write this out. Dr d theta, that's the 4 cosine theta times sine theta plus cosine theta times r, and r is 4 sine theta. On the bottom, I have dr d theta, which is our 4 cosine theta, times cosine theta, plus, no, minus sine theta times r, and r is 4 sine theta. And this is what dy dx is, right? Dy dx is given by this formula right here, all right, which we did. We differentiated it using product chain, etc. rule, and using the fact that r is equal to 4 sine theta to plug stuff in. I mean, we do have to simplify this, but that is how you're going to find the derivative dy dx. if the equations in polar coordinates, in their polar equations, right? So I'm not sure how much I want to simplify this on this video, since we're really just trying to focus on uh, doing the calculus of polar equations. But I get 4 cosine sine plus cosine theta 4, so that basically they're the same. I get 8 sine cosine on the top, because I'm just adding 4 sine cosine twice. On the bottom, I get something more complicated. I get 4 cosine squared theta minus 4 sine squared theta, which does simplify if you know your trig formulas, but I'm just going to leave it there for what dy dx is, because I don't want to go down that rabbit hole of trying to simplify this using all those different formulas. Okay, so that's how to find the derivative dy dx if you know a polar equation. R is equal to 4 sine theta was the one we did as an example. All right, so the last example here is to find the derivative dy dx of r equals theta squared. So I'm going to make sure that's my last page. Yeah, that's my last page. So I was trying to remember if we did, we're going to do arc length and stuff like that in the next video in 10.4. We just do the derivatives in this one. Okay, so find the derivative of r is equal to theta squared. Again, good time to practice if you want. Pause the video if you desire, and then I'm going to write out the solution here. So we're looking for dy dx of r is equal to theta squared. And you can do all these steps again, but if you just have this formula written down, it's always going to be the derivative of r sine theta on the top and the derivative of r cosine theta on the bottom. So we know that dy dx, no matter how many steps you want to show, is going to be dr d theta times sine plus cosine theta times r over dr d theta times cosine plus, no, minus, right? Because we have a minus there, minus sine theta times r. Now, this formula seems like completely bizarre. If you just memorize this formula and you don't remember where it comes from, it's going to be like, what? Why is that the formula for dy dx? It just seems to be out of nowhere. But it's not out of nowhere. It's just literally the derivative of r sine theta over the derivative of r cosine theta using the product rule, right? So that's all it is. It's just a product rule of the y equals r sine theta on the top and the x equals r cosine theta on the bottom. All right, so we do have to find out what dr d theta is. We are given that r is equal to theta squared. So dr d theta is just 2 theta. And then I can just start plugging stuff in. So what do I get? If I get dy dx is equal to dr d theta, which is 2 theta, sine theta plus cosine theta times r is theta squared. I'll put the theta squared in front. And then on the bottom, I have dr d theta, which we know is 2 theta times cosine theta, and then minus sine theta times r, which is just theta squared. And nothing much to simplify here. That is your answer for dy dx when r is equal to theta squared. Okay, so some derivatives of polar equations. Great. Well, hopefully this was useful. Hopefully you learned a little bit about polar equations and how to do a little bit of calculus on them. If you do have any questions, please do reach out. Please email me or stop by my Zoom tutoring hours, and we'll get you going and answer whatever questions you have or any what ifs. I hope you have an enjoyable day, and I hope I see you in another video or maybe even in Zoom.